Morning, everyone. So we are coming pretty close to the end of our chapter one. We've been looking at reaction kinetics, basically the speed of a reaction. Yesterday's lesson, we started looking at kinetic energy distributions. So even though we are at some set temperature, which measures our medium or moderate pace, at any given time, we always have some particles that are traveling faster, some particles that are traveling slower. So I'm just going to give you a quick example of that one there, and then we'll go on today to take a look at mechanisms. Let's just start off with the warm-up. I want you to explain using a KE distribution and PE diagram why reactions are generally slower at colder temperatures. So let's just have a look here. So experimentally, it's actually quite simple, right? So we have a container. Right now here it's cold, right? We have a fixed number of particles inside. What we know is when we have a cold temperature, we know that we have very slow moving particles, right? But even though the temperature gives you a sort of a medium speed that the particles have, we actually want to figure out at this point how many are fast moving, how many are actually slow moving. So when I plot a KE diagram here, let's compare this here to actually a room temperature, right, or a hotter picture. So let's use our KE distribution here. KE distribution plots the number of particles, plots it against the kinetic energy. Again, kinetic energy here is the moving energy. So on the far side here, it means fast. On the close side here, it means slow. At room temperature, our curve would look something like this, right? At any given time, our average speed, right, it's like most particles are traveling at this medium moderate pace here. What's going to happen to this container? I might still have the very same number of particles. What happens to this as I change from a room temperature box into a colder box here? And as I steadily step over to a colder box, I know what's happening here is I'm cooling down the system. I'm stealing away some of the kinetic energy that the particles have. The particles are going to get a little bit more sluggish. So this time, instead of the curve shifting over to the right, this time the curve is actually going to shift over to the left. Again, they're going to shift over by different amounts. It's not just like a simple transcribe of that graph like that. They actually shift in such a way that the average speed definitely decreases. So most particles are actually now going to travel at an even slower speed. But even then, I may have some moderate pace here. I still going to have some that are super duper slow, some that are not as fast anymore. So my curve here has actually shifted over in the opposite fashion here. We had an activation barrier. We had sort of an energy requirement. It was only the particles that had enough energy that could react. If you compare the room temperature curve here with the blue in the colder case here, we see that the number of particles, even at a slower speed, even at a colder temperature, I still have some particles that are moving quick enough, but definitely not as many as I had before. So in this case here, it's important for you to know the reaction could still occur at cold temperature, but at a colder temperature, we have less particles with sufficient energy. Again, it always comes back to those two features. Is it an energy argument? Is it a geometry argument here? With sufficient energy to overcome the activation barrier. Right? The activation barrier stays fixed. It's the same hill that you need to surmount, but it's just now we have even less particles, even less fast-moving particles to actually collide. They need to trade in enough of their kinetic energy to become potential, but I don't have a lot of them that can end up doing that. Remember, for a rule of thumb, what we did is we ended up saying for every 10-degree change, it usually doubles the rate. So if I just put some numbers to this, just argument's sake here, let's say at room temperature, given at temperature of 20 degrees, let's say the rate was measured to be 1.6 times 10 to the negative 3 gram per second. Right? So they just randomly list off that number there. What if I cool this down to 0 degrees? Right? So cooling it down to 0 degrees would be dropping it 10 degrees once, dropping it 10 degrees again. Using the rule of thumb here, if an increase of 10 degrees for a slow reaction doubles the rate here. You can imagine the rate divides by 2 for the first part, divides by 2 again. So if you have nothing else to go on, 1.6 e negative 3 divided by 2. This one gives you here, you can even say 0.8 times 10 to the negative 3, or your calculator will give you 8 times 10 to the negative 4, divided by 2 again. So this one here is 4.0 times 10 to the negative 4. Again, this is only if you have nothing else to go on. You have no talk of changing the number of particles, changing any of the other factors here. If you just had a numerical value and you're just interested in as this 10 degree changes, you can, just as a rule of thumb here, by just doing the math here, every time you decrease by 10 degrees here, the curve shifts enough that actually halves the number of particles. So it decreased the rate by half. Right? So in today's lesson here, we're going to visit something we call a reaction mechanism. So it's actually the mechanics or the mechanism of a reaction. The way I want you to think of this mechanism here is, for a reaction, a mechanism actually lists for you the actual sequence of steps. The actual instructions: do this part first, do this part first, and then do this part first. So just as an analogy, let's say we were building a house. If you're building a house, you would lay your foundation first. That's step number 1. Maybe you set up a wooden frame of your building, step number 2. Then you put up your roof. So there's sort of an ordering of steps, 1, 2, and then 3. In the same way, chemical reactions, when they collide, they can also occur in multiple steps. I've been somewhat simplifying things a little bit when I've been giving you reactions like, let's say H2 runs into Cl2. We've seen this reaction quite a lot in here. I've been giving you the overall. I've been giving you, in our analogy, this is like build a house, right? Well, you might be like, well, where do I start, right? It's possible that in this chemical reaction, it's possible this may actually take 5 steps, 5 individual reactions to you overall to give this reaction. The reaction as given to you here, this is referred to as the net equation. This is the overall equation. This is what eventually the task is going to be, but I might need in a mechanism to actually give you the details, give you the actual steps of what's happening behind. They will not ask you propose a mechanism from scratch. You can actually do a whole master's thesis to actually find out an exact mechanism. But if they give you a lot of details, they give you most of the mechanism, they can ask you for the little bits. All right. So just as we start off here, this one here is not likely to take many steps, because what this is referred to as a 2-particle collision. 2-particle collisions are very likely. Remember, for a successful collision, right, that's always what we're after for a reaction to occur. For a successful collision or for a successful reaction, we needed the 2 features. We needed to have sufficient energy. We needed to overcome that energy barrier, and we needed to have good geometry, favorable angle of hit. So in this case here, the H2 is diatomic, so it's H and H. The Cl is diatomic, C on Cl. All I need is for these 2 particles to actually collide. Right? It's just 2 of them. They just have to get to the same spot in space. They have to arrive at the same time, and they just need to check the conditions. Do you have enough energy? Yes or no? Are you coming in with good geometry? Can you overcome this energy barrier with the orientation that you're in? If you can, done. The reaction is going to break bonds, form bonds. We're going to have created a new molecule. Right? So 2-particle collisions are very, very likely. Let's make it just even 1 step harder. So just as an example, let's consider a 3-particle collision. So A plus B plus C, let's say they all collide and they synthesize and they just become ABC together. All right? This one here should actually surprise you. Why does this one here happen at all? Because what I'm suggesting to you here is, inside my container, we have a bunch of A's, we have a bunch of B's and C's, right? They're all traveling at different speeds at first, okay? First thing is, I can have 2 particles collide. A might collide with B, but if there's no C, no reaction. B might collide with C, but no A, no reaction. So I may have a bunch of 2-particle collisions. Those are all really likely. For this to actually occur, and especially if I'm proposing a 1 step, what I need them to happen is I need them all to hit the same spot in space. I need A, B, and C at the same location at the same time. And not only that, this might still happen, although not as likely as a 2-particle collision. It has to make sure that it has to be the fast-moving A, the fast-moving B, and the fast-moving C, right? All these layers here are making it probably not going to happen as easily. So Again, they've done the math of this one here, even for a 3-particle collision, let alone some collisions propose 10-particle collision, 20-particle collision, right? It's just not going to happen here. When they did the math, it's about 1,000 times less likely than a 2-particle collision, since 3 particles need to collide. So what that implies here is they have to be in the same location at the same time, right? So that's already hard enough. And not only that, remember we also have this energy argument here. If I happen to have even one of these particles being slow, the other 2 could be fast. Oh, I still don't overall have the activation barrier, no reaction. So need to collide, that's one problem. That's already hard enough. And they also have this problem with sufficient energy. I need to have the fastest moving ones of all 3 particles. Not very likely going to happen, right? So how is it that this one actually happens? So again, we might propose to you this as the overall reaction. The building the houses A, B, and C has somehow actually combined together to form ABC. What I can list for you is this actually doesn't take place in one step. This one here, as a mechanism, as a listing of steps, maybe what I propose to you, step number 1, maybe A and B just have to collide first. A and B collide together, they're going to form AB, right? As step number 2, after you laid the foundation of the house here, you start framing the building here, maybe then AB needs to collide with C and then becomes ABC, right? So what I've done here is I had an overall reaction. I had a net reaction. This is my build the house. But what I did here is I actually separated. Well, you do this part first. Let's let A and B collide. Is this one likely to happen? Well, much better than the first case. Instead of being 3 particles all in the same spot, all in the same time, I only need 2 particles collide. 2 particles collisions are going to be 1,000 times more likely. So A just needs to collide with B first. They have to come in with the right energy. They need to come in with the right geometry here. They form AB. And then what's going to happen in step 2, you're going to take the AB that you sort of laid down in the first step, and the AB as a molecule then just needs to collide with C. Again, another 2-particle collision in this case here. So each step is called an elementary process. Each step is called an elementary process. We're using the word elementary as in, oh, it's the basics. It's the details. It's the, this happens first amidst the building the house project. So each step is called an elementary process. And in our proposal here, and is more likely since it needs only 2 particles. So back to our 2-particle collision case. 2 particles to collide. Still the same requirements with enough energy and good geometry. Remember, we call that collision theory. That part just comes throughout this chapter here. All right. Now, what's interesting here is, although I do have some overall reaction, I called it the net reaction earlier, maybe you call it the overall as well, you'll notice when A and B collide, this one here itself is a reaction. This one here itself is a reaction. So even though I may have one overall project, in the end I want to see A, B, and C join together to become ABC, I've broken that up into different steps, each of which are a reaction. So in this case here, each step has its own activation barrier because it is a reaction in itself, right? We're going to see catalysts come in tomorrow's lesson. It's actually going to provide a way that has smaller activation barrier. If I make the reaction a little bit easier to occur, if I don't need to be the really fast moving particles to actually collide, that will actually speed things up. More on that tomorrow. When I deal with a mechanism here, usually your steps here, even though both of these are 2-particle collisions, they're already going to be more likely than 3 all at once. Usually one of them is going to be slower than the other one. It's not always easy to identify which is going to be slow, so they usually need to tell you which is slow. Let's say for argument's sake here, the first reaction is slow. The one that they label to be slow is given a special name. This name here is going to be called a rate determining step, or a RDS for short, rate determining step. This is the step that determines the rate. This is the step that controls how fast you can do your procedure. So let's switch over to an analogy. Let's say we worked at McDonald's. Let's say step one is let's cook the burgers, and then step two is let's just assemble the burgers. Okay, so step one, obviously, cooking takes longer than assembly. So if you're in the sort of McDonald's business here, you're trying to get clients buying food and having really fast turnover, your overall business is limited by how fast you actually can cook the burgers. You wouldn't bother hiring more people to assemble burgers because all the people that are waiting to assemble are just waiting on the cooks, are waiting for the burgers to actually cook. If you were to invest in anything, you would invest in maybe more ovens, maybe more chefs, maybe more people actually doing the slowest steps. If I have more capacity to cook more burgers, then the assembly takes a split second in comparison. Basically, if I can speed up the rate determining step, I can overall speed up my business of getting burgers out to the people that want them, right? So usually in a mechanism, again, the mechanism is the actual sequence of steps. Usually one step is slower than the other one. It's always the slowest step. That's the sort of limiting feature here. This is the thing that's keeping your business running slowly. If you were to invest anything, you want to speed up this step here. So let me just write that down for you here. Rate determining step here. It is the slowest step. In terms of activation barrier, do you think it would be the high barrier or the low barrier? Right? If it's a high barrier, that means not a lot of particles can actually react. That makes it slow. If it's a low barrier, a lot more particles can collide. So in this case here, our rate determining step, this is the step with the highest activation barrier. So this is the slowest step. This is slowing down your overall production. It doesn't always need to be step one, but in this case here, it's a step with highest activation barrier, and it limits the overall rate. So if you could somehow speed up this one step, right, you can speed up the overall rate. So if I can hire 10 people cooking patties and there's one person assembly, well, the assembly is really quick in comparison here. That's perfectly fine. There would be no point in me hiring 10 people to assemble the burgers and just one cook. I'm waiting for the patties to cook. There's not a lot of people working that station there. That's going to be really slow. I want to increase the slow step to overall speed up the reaction. So if I plotted a sort of potential energy diagram for this one here, because both of the steps are a reaction in themselves, both of them have an activation barrier, we're looking at something like this, where we have potential energy, we're going to plot against reaction. This time I need to plot, yes, overall, again, I don't know necessarily, let's say A, B, and C. Yes, overall, you're going to end up forming ABC. I don't know if it's endo or exo. Let's just, for argument's sake here, let's say it's endo. I actually broke this, well, 3 particle collisions all at once here is not very likely. The energy hill may be ridiculously tall. What I've done in this case here in showing you the mechanism is I've actually showed you it actually takes place in 2 steps. The first step has a relatively high barrier. It's the one that's the rate determining step. This activation barrier here actually makes it really hard for A and B to first combine together. The C actually didn't do anything. And maybe in the next situation here, the A and B can collide with C pretty easily. Maybe they have another energy hill and they actually eventually get over to ABC. Whenever we're interested in doing activation energy, remember we plot a line over, we prop the reactant line over, and we point towards the top of the hill, the activated complex for that hill. That's the activation barrier for step 1. This is high. This means it's a very slow step. This is the rate determining step. Once the AB ends up forming, the assembly of the burger is really quick. Let an AB run into C. It also does have an energy requirement. Every single reaction will have an energy requirement, but you notice this activation energy barrier, I'll call it EA2, is less than EA1. This one here will be faster. The assembly pretty much takes no time in comparison to waiting for the burgers to actually cook. All right? So we talk sort of in general here. Let me just give you a feel of what a question might look like. So as an example, let's start off with 4HBr. It's going to collide with O2. This is going to become 2H2O and 2Br2. This is the net reaction. This is the overall reaction. Now we know our reaction depends on just the reactants. So we know the left-hand side are reactants. Our speed of getting the HBr to collide with O2 just depends on these guys. It could care less what the products actually are. This one here is proposing a 5-particle collision. 4 HBRs need to collide, same spot in space, same time, not very likely, even less likely than 3-particle. 5 particle collision is very unlikely. So that sort of hints at maybe this actually takes place in multiple steps. Again, you don't need to design a mechanism from scratch. I'm going to give you some of the details. So the first step in this mechanism here, we actually just need one of these HBRs to react with an O2. This ends up forming Huber. This one here is known as the slow step. Again, it doesn't always have to be the first one, just for argument's sake here, that one was. Second step here, we take this Huber, HOOBR. This one here needs to collide with yet another HBr. This produces 2 Huber. And then step number 3 here, this one requires 2 Huber and 2 HBr. This one ends up forming your 2 waters and your 2 Br2. Right? So I've actually given you all the details here. They could have just, given you this mechanism here. Can you tell me what the overall reaction is? Each step is an elementary process. Each step has its own activation barrier. But what you'll find is instead of having 5 particles collide all at once, the first 2 steps are just 2 particle collisions. Now we'll also see something interesting here. Usually I would imagine, well, 2 particles likely, 2 particles likely. Wait, step number 3 actually involves 4 particles. This one here should be the slow step. And yet when they told us our rate determining step is the one that's the highest activation barrier here, it was actually the 2 particle collision. That may be because not just the number of particles that need to collide together, but that may be because HBr and O2 have a very strong bond. O actually has a double bond. Maybe breaking that bond here is a lot harder. So I know that's the slow step that was given to me. I know this is the one that has the highest EA. And maybe in this case, it's not because of the number of particles that need to collide. Maybe it's the one that actually has the strongest bonds. Maybe the ones that doesn't break easiest. But nonetheless here, we couldn't predict that. Even as I look at step number 3, I might say step number 3 might need to be subdivided into many more steps. Maybe I don't really have 4 particles colliding at once. Maybe some of them collide in 2 particle collisions. But at least this is the detail that they're giving me. How do you find the overall reaction? Well, since these are all sort of reactants in their own respective steps, reactants should end up on the left side. These are all in the products. They should end up on the right-hand side. So it's just a matter of dragging everything on the left to the left, the right to the right. However, we're going to see chemicals that appear, and they're actually going to cancel out. For example, HBr and O2 first create a guy called Huber. I don't actually have Huber in my overall reaction. That's because Huber was actually used up in step number 2. Something that gets created in one step and used up in another, instead of writing Huber on both sides, that just cancels it out. Chemicals that do that are referred to as reaction intermediates, or just intermediates for short. Reaction intermediates are species, are chemicals, species that are created in some early step, but consumed in a later step. It does not have to be necessarily the step immediately after. It doesn't have to be, I created in step 1 and I have to use it in step 2. If I use it up in step 3, it's still called an intermediate, and overall, it actually doesn't appear. So Huber is an example of an intermediate. Can you give me an example of another intermediate in this mechanism? Well, in the same way here, the 2 Huber, which is actually the product of step number 2, the 2 Huber gets canceled out here by this 2 Huber here. If the numbers didn't match up, I had 2 Huber and I have 1 over here, I would still cancel one of them, right? But nicely, 2 and 2. So those 2 cancel out here. It was created in an early step and used up in a later step. The Huber as a chemical, I know I had 2 of them in the balancing, but Huber as a chemical is also an intermediate. Those also don't appear overall. Those should be my only intermediates in this setup here, and therefore all I'm going to do is I'm just going to combine them together. In total, I have HBr, HBr, 2 HBr, so I have 4 HBrs in total. I'm going to react with O2. I'm going to produce 2 H2O and 2 Br2. Even though I might refer to Huber and Huber as products of their own elementary steps, they are not an overall product in the net reaction because they don't stay left over. So it's only after you cancel out, then you can identify who are really reactants, who are really products here. If you really match it up as earlier here, it exactly matches here in terms of numbers, in terms of what's on which side. So all I've done here is I've given you an overall reaction. A 5 particle collision is not very likely, but if I break this down into 3 steps here, you can sort of work your way around what it's going to be. Let's plot this out on an energy level diagram. So we have an energy level diagram. We're going to plot PE against the reaction axis. And what's going to happen here is we're going to have an activation barrier for each of these. The first step, again, happened to be the slow step. So this one I'm expecting to be the highest activation barrier. I don't, again, necessarily know which one is exo or endo. It could be exo, but it could still be a very high activation barrier. Let's say that's for step number 1. So step number 1. Step number 2, right? We take the Huber, in comes another HBr here, another energy barrier. Step number 3, also another energy barrier here. Eventually, what's going to happen is I'm going to start from my reactants, start from the 4-HBr and the O2. I'm going to eventually get to, let me just get just a little bit higher here. Like overall, it could be end or X, so I'm not really sure. Let's do it like that. And basically, we're going to end up with products. If I wanted you to calculate a delta H of the overall, you would still sketch in. Well, the reactants started off going here, and in this case here, maybe delta H is endo, maybe it's exo, I'm not really sure. That's delta H. What I want to show you on this diagram here is each step in the elementary process, each step in the mechanism, called the elementary process, each step has its own activation barrier. So this one is EA for the first one, that's the largest one. This one here is a little bit smaller. This one here is a little bit smaller. So definitely the EA1 is the one that's the highest. All right, so I'm going to leave it off at that there. I'm going to leave you with a question just to think about. How is, I'll answer this tomorrow. How is an intermediate different from an activated complex? Right? Because they're different, right? If they were the same, I'd just give it the same name, right? So think about where an intermediate might show up on this curve and where an activated complex shows up on this curve. And I'll pick it up from there tomorrow. Thanks, guys.